In this lecture, we shall consider tests concerning mean and variance of a univariate normal population. So we will consider tests for mean and variance of a univariate normal population. First, we will consider one sample Z test. One sample Z test usually referred to as a one sample Z test for means, which is used to test the hypothesis about the sample belonging to the population, given that the standard deviation of the sampling distribution is known as a function of the population standard deviation. That means basically the sampling distribution standard deviation has to be known in this situation. And here Z will refer to a standard normal distribution. Now we will go into the characteristics of this Z test and the procedural details of this test. And it is a test for means. We recall that the sampling distribution represents the distribution of different samples taken from the population to perform the hypothesis testing. In earlier lectures, we considered this. So basically, we considered the sampling distribution of a statistic, which is nothing but the probability distribution of the statistic. One sample Z test for means involves comparing the sample mean with the known population parameter mean. That means whether the sample mean is equal to a given population mean. In other words, we use Z test to test whether the sample belongs to the population or comes from a population on the basis of Z statistic or Z score. These are nothing new. We have already considered Z statistic or Z score in terms of a standard normal variate. The null hypothesis is set as the claim that the sample belongs to the population and there is no difference between the sample and the population. No difference between the sample and the population basically in terms of its mean. Based on the value of the Z statistic or Z score, we determine whether to reject the null hypothesis or otherwise to accept it. That means whether we say that the sample mean is not a sufficient evidence to say that the population mean has got the specified value or not. Here we need a Z distribution or a standard normal distribution and see whether the Z statistic falls in the critical region or in the acceptance region. There are several assumptions of a single sample Z test. Every statistical method has got assumptions. Unless these assumptions are satisfied, the tests cannot be carried out, or even if carried out, the tests will get erroneous result. The assumptions for a single sample Z tests are continuous, that is continuity, normality, that is normally distributed. The data has to be a random data, that means the sample has to be a random sample, and we have enough data to conduct the test. We shall describe these one by one. First, we come into the continuity. The variable that we are talking about, and we want to see whether the mean is different from the population mean, has to be continuous in nature. Continuous means the variables can take up any reasonable value. That means it can take up an uncountably infinite number of values within its range of variation. Now you see, this is a very valid assumption because unless the data is continuous, we cannot assume that the random variable under consideration or the test statistic under consideration follows a normal distribution, because we know that normal distribution is the distribution of a continuous random variable. So this continuity assumption has to be satisfied. Next is that the statistic or the data have to come from a normal distribution. The variable that we care about must be spread out in a normal way. In a normal way means the data has to have a normal distribution. It must look like a bell-shaped curve and a symmetric one. When we plot the data in a graph, we only use a single sample Z test with our data if the variable is normally distributed. So unless the variable is normally distributed, we cannot perform a Z test. Now, whether a data is normally distributed or not, to understand that, there are several other sophisticated tests like Shapiro-Wilks test. We also can form QQ plots, but these are out of the scope of our syllabus or our course of study. So we will assume that the data comes from a normal distribution. At the most, what we can do, we can plot the data graphically, as I have said, and we can see whether it resembles a normal curve. Most importantly, the sample we'll draw has to be a random sample. The data points for each group in our analysis must have come from a simple random sample. This means that if we wanted to see if drinking sugary soda makes us gaining weight, then we would need randomly select a group of soda drinkers. And for our soda drinker groups, then randomly select a group of non-soda drinkers and our non-soda drinking group. So these are very important. That means we have allocated our sample randomly. Unless we allocate them randomly, we cannot go for any test. Forget about Z test. We cannot go for any test. The key here is that the data points for each group were randomly selected. This is important because if our groups were not randomly determined, then what will happen? The analysis will be wrong. In statistical terms, this is called bias. That means our decisions will be erroneous and biased. Or this will have a tendency to get incorrect result, even if the sample is not a random sample. So can you think of a situation when the sample is not a random sample, what kind of error we may get? Now see, if the data is not random, what will happen? Suppose we are testing for means. So suppose we are testing for mean average income. Then if I select purposely those individuals who have very high income, then obviously the result will be erroneous. That means we will conclude that the population mean is not equal to the specified value of desire. So obviously the sample has to be taken in such a manner that the sample becomes a random sample. We should have enough data to perform the test. Enough data means we have to take care of our sample size. The sample size for the analysis should be at least 30. It really depends on the expected size of the different groups and the population value. This will determine the sample size. But on an average, if I can take more than a 30 plus type of sample size, then we can perform this Z test satisfactorily. Now we go into the mathematical formulation of the test. We consider a normal population, that is a population which is normally distributed with mean mu and variance sigma square, where mu is unknown and sigma square is known. Definitely mu has to be unknown because we are testing for mean. Had the mean been known, why should we go for test? We are going for testing for mean because the mean is unknown and we are testing whether this mean has got a specified value. That is given in the null and the alternative hypothesis. Here our problem is to test H0 mu is equal to mu naught against H1 mu not equal to mu naught, where mu is the population mean and mu naught is some specified value of mu. Now, instead of a two-sided test, we can have one-sided test like mu greater than mu naught or mu less than mu naught, depending on the situation. We have a random sample x1, x2, xn drawn from the population, random sample, and we calculate x bar, the sample mean. The test statistic will then be given by square root of n into x bar minus mu naught by sigma, which we denote by t say. Now, the value of this test statistic will tell us whether to accept or reject the null hypothesis. And this t under H0, that is assuming H0 to be true, will follow a standard normal distribution. Now, what I mean by saying that assuming H0 to be true, assuming H0 to be true means here in this situation of a Z test that the mean is equal to mu naught, the specified value. And we reject H0 against H1 if the absolute value of t is greater than Z alpha by 2, where Z alpha by 2 is the tabulated value of a standard normal variate Z with level of significance alpha. There are various limitations of this particular test. Let us see them. Sample sizes may range from a few to several hundred. If our data are discrete with at least 5 unique values, we can often ignore the continuous variable assumption. Even with discrete data, we can perform this test, but they have to be 5 unique values. The greatest restriction is that the data come from a random sample. Unless the sample is random, this test is going to give us erroneous result. That means when H0 is to be accepted, that may be rejected, and the other way also. That means we will make an incorrect conclusion in that situation. We take an example. A teacher claims that the mean score of students in his class is greater than 82 with a standard deviation of 20. If a sample of 81 students was selected with a mean score of 90, then we have to check if there is enough evidence to support the claim at 0.0% level. So here, if mu is the mean score of the students, we are going to test whether mu is equal to or greater than equal to 82. That is the claim of the teacher. And 81 students were selected in sample, and this sample has to be selected randomly, and it is found that their mean score is 90. And one thing is important, here the standard deviation is given, which is 20, and we will perform this test at 5% level of significance. As the sample size is 81 and the population standard deviation is known, so this is an example of a right-tailed one-sample test. Why right-tailed test? Because we are going to test that whether mu is greater than 82. So right-tailed test, one-sided test. From the Z table, we can find the critical value at alpha equals to 0.05 is 1.645. That can easily be found out. And basically we are testing mu equals to 82 against mu greater than 82. The test statistic, we know the test statistic rooted into x bar minus 82 by sigma. Here n is nothing but 81 because the sample size was 81. X bar we can calculate, it's given actually, and sigma is known. And the value comes out to be 3.6. Now what is the critical value? The critical value is 1.645. As 3.6 is greater than 1.645, what we do? We reject the null hypothesis and say that the claim of the teacher is justified. So that means we say that there is enough evidence on the basis of the sample to support the claim of the teacher. Next, we go to something called one-sample t-test. In one-sample z-test, the population standard deviation was known. Now, in any real-life situation, nothing will known about the population. The population mean will be unknown, population standard deviation will as well be unknown. So in this situation, how can we modify the test? Can you give me any idea how we can modify the test when the population standard deviation is unknown? So we come to a one-sample t-test. The one-sample t-test is used to compare sample mean to a specific value, that is a population parameter. It may be a neutral point on a Likert type scale, chance performance, so on and so forth. So basically, the objectives of z-test and t-test are same, but there is a difference in terms of population standard deviation. Here the population standard deviation is unknown. This test is also known as student's t-test. We can think of some examples. A study investigating whether stockbrokers differ from the general population on some rating scale where the mean for the general population is known. In this situation, we can use a t-test. An observational study to investigate whether scores differ from chance. This is also a suitable example of a t-test. In both these situations, you see nothing has been told about the population standard deviation. And here we are measuring the difference or testing the difference in terms of their means. So that is why these are suitable examples or suitable fields of applications of one-sample t-test. Requirements and assumptions of a one-sample t-test. We have already seen z-test has got some requirements. There are some assumptions on which they are based. So obviously t-test will be based on some assumptions and some requirements. A one-sample t-test should be used only when the data has been collected on one variable for a single population and there is no comparison is made between groups. That means here we do not want to compare the mean score of two groups. Obviously, we will take up this issue in a later lecture material, but not in this one. Here we are concentrating on a one sample situation. That means we have a single population and from which we are getting a sample. And from each sample observations, we are studying the values of only one variable. This is important. Independent values that are not related to one another. The one sample t-test assumes that all errors in the data are independent. Now what do we mean by these errors? The term error refers to the difference between each value and the group mean. This is basically what we call errors. And one sample t-test demands that these errors are independently distributed, because the result of a t-test will only make sense when the scatter is random. That whatever factor caused a value to be too high or too low, that affects only that one value. It does not affect the other values. So in this sense, the values are independent of one another. And if the values are independent of one another, the scatter plot will show a random nature. The scatter plot means we'll simply plot the data that will show a random nature. So this is very important, that the errors will be independent. That is the observed value minus the group mean. So for each observed value, we'll find out these errors. So if there are n such observed values, we'll have n such errors. These errors have to be independently distributed. The measurement has to be continuous, similar to the z-test. A t-test is only appropriate to apply in situations where data represent variables that are continuous measurements. Now, as they rely on the calculation of mean value, variables that are categorical should not be analyzed using a t-test. Categorized means we can categorize a number of observations. Suppose we can collect data on income. This income is a continuous variable, so we can use these income figures in t-test. But if we categorize this income as, say, rich, moderate, poor, then they will not remain continuous variables. They will become categorical variables. So in such situations, we won't be able to apply t-test. That means whenever we have some measurable data on a continuous variable, we have to use the values only. We cannot categorize them. This is very important because one may categorize a numerical data, but if we do that, we cannot apply t-test. The data must be obtained from a random sample of the population. As we mentioned earlier, unless the sample is random, we will go on to erroneous result. The same thing can happen as I mentioned in case of Z-test. If we are testing for whether the average income is equal to something, and if I select only the rich people in my sample, one by one, then obviously the conclusion that we will draw will be very much erroneous. Similarly, if we take only those people who are under the poverty line, obviously the result will be erroneous. So we have to take a random sample so that people from all possible income category may come in our sample. The data has to be normally distributed as well. As with all parametric hypothesis testing, the one sample t-test assumes that you have sampled your data from a population that follows a normal distribution or a Gaussian distribution. With this assumption, it is not important with large samples, but it is important with small samples. When the sample size is less than 10, the data has to be normally distributed. If you can recall, when we studied chi-square T and F distributions, we said that these are the sampling distributions arising out of a normal population. So, unless this population is normal and the sample is taken from a normal distribution, then we cannot apply t-test because the test statistic will follow a t distribution, which is essentially a sampling distribution derived from a normal population. Now we go into the mathematical formulation. We consider a population with mean mu and variance sigma square, where both mu and sigma square is unknown. So can you find the difference between the z-test and t-test here? While I read the sentence once again, consider a population with mean mu and variance sigma square, where both mu and sigma square is unknown. Try to look at the difference from the z-test. So here you see the basic difference between a z-test and t-test is this. Here we have said both mu and sigma square are unknown. But in case of z-test, we said that only mu is unknown, sigma square is known. The problem remains the same. We test h naught mu equals to mu naught against the alternative mu not equal to mu naught. Here also we can have one-sided tests like with alternatives mu greater than mu naught or mu less than mu naught. We have a random sample x1, x2, xn. X bar is the sample mean and s square is the sample variance. The test statistic is root n into x bar minus mu naught by s equals to t say, and we reject the null hypothesis h naught if modulus of t is greater than t alpha by 2, where t alpha by 2 is the tabulated value of t with level of significance alpha. These tabulated values of t can be found out from t table, and it is available in softwares also. Given the value of alpha, we can easily find that out. Now we try to understand this graphically. Systolic blood pressure before and after the treatment. So suppose we know that the systolic blood pressure will reduce after the treatment. So that means post blood pressure will be less than the pre-blood pressure. That means you see, we assumed a normal distribution. So the normal distribution will shift towards the right. That is what we are testing. If the mean value decreases, the shape of the distribution will remain intact, but will shift towards the left. That is the thing. So that means the blue one is before the treatment and the red one is after the treatment. So you see the red one is towards left, that is the mean value is decreased. We take an example. Suppose a professor wants to know if her introductory statistics class has a good grasp of basic maths. 6 students are chosen at random from the class and given a maths proficiency test. The professor wants the class to be able to score above 70. The 6 students that the professor had selected, they scored 62, 92, 75, 68, 83 and 95. 6 values are given. Can the professor have 95% confident that the mean score for the class on the test will be above 70? So that means the professor wants that the mean score will be above 70. He has taken a sample of size 6 and he has got the marks. So he is going to test whether the mean score is above 70 with 95% confidence. That means the level of significance is 5%, that is 0.05. So the null hypothesis is mu equals to 70 and the alternative is mu greater than 70. So it is a one-sided test. To be specific, a right-tailed or right-sided test. We know the test statistic, root n into x bar minus mu naught by s. N is the sample size, here it is 6, x bar we can compute, the values are given, mu naught is 70 and the standard deviation is to be calculated. Now mind you, here s square is 1 by n minus 1 summation xi minus x bar whole square, not 1 by n. In connection with t distribution, we said that we will take the sample variance as 1 by n minus 1 summation xi minus x bar whole square. The critical value of t, that is the tabulated value of t, we can find out 2.015, while the value of the test statistic has been found out to be 1.171. So t is less than the critical value. So what we do? Should we accept or reject the null hypothesis? Since t is less than the critical value, we accept the null hypothesis. So that means, what do we mean by that? Can we say that the professor's claim is justified? That is, the average score in English is greater than 70? No, we cannot say that, because my sample tells me that H naught is accepted. That means the mean score is greater than 70. We cannot say that. Now see, here again I will point out one thing, that had the sample been different, we could, if we had selected 6 other students, then their scores could have been more and the value of the test statistic could have been more than the critical value. Then we could have rejected the null hypothesis. Unlike what we are doing here, accept the null hypothesis. So these things are to be kept in mind very carefully, that change of sample may lead to the change in the conclusion. So whatever sample we have, we stick to that sample and we will make our decision in that matter, and there will be bad luck if we get an erroneous result, but we cannot do anything for that. So we have to stick to the sample that we have in our hand. In the next segment, what we will do, we will take up some numerical illustrations on Z and T test, and then we will go over to 2 sample T tests. Thank you.